So I'm going to do 3 more problems in real analysis, but before I start that, I just want to let you know that I will be doing the Q&A session on Sunday. So if you have a question that you want me to answer, I made a post to my community tab a few days ago where I thanked everyone for the 10,000 subscribers. And if you wanted to ask me a question, you could put it there. So if you haven't seen that post yet, put your question there and I'll look at it. And hopefully I'll be able to answer it because a lot of you have asked a lot of questions and I'm very grateful that you're interested in knowing about my PhD program. So if you have a question, please post it there and I'll read it and address it on Sunday. Okay, so the 3 problems that I've picked for tonight are relatively easy problems because I'm feeling a bit burned out recently and I don't want to be pushed that hard anymore. So what problem are we looking at here? We have a function that is Borel measurable. It maps the unit interval to the unit interval. So everything's happening in that square. We assume that the integral of f from 0 to 1 dm is equal to I, which is a positive number. We want to prove that the measure of all points where f is greater than I over 2 is bounded below by I over 2. This was an old qualifier problem, but it was also given to us as a homework problem last year. So let's do it. So this problem is kind of nice because it doesn't really have any tricks in it. Just as long as you understand the basics of integration, this problem is pretty straightforward. So what do we have? Well, we have that the integral from 0 to 1, I can split this integral up into 2 pieces. I can call it integral f 0 to 1 times the characteristic function of f equals 0 dm plus integral 0 to 1 f times the characteristic function of f positive. So I've split this integral into 2 pieces. This characteristic function acts like a light switch. It turns the function on when you're on this set, and it turns it off when you're outside that set. And I've split the function into 2 pieces, essentially. So this turns the function on when f is equal to 0, and this turns the function on when f is positive. Remember, f is all in that square. But this is kind of stupid, right? Because if f is equal to 0, then that means this whole integral here has to be equal to 0. So all of the stuff that's happening happens over here. Okay. So let's call this integral I, for example. Let's say f is equal to 1, or 0 to 1, and it's equal to the integral f characteristic function, f positive, dm. And we can further split this integral up in another way. So what I can do is call this integral 0 to 1 f characteristic function. And I want to look at the part where f is bigger than I over 2 dm plus integral 0 to 1 f characteristic function 0 less than f less than or equal to I over 2. So what have I done? I've taken this set and I split it up into 2 pieces. The part where it's bigger than I over 2 and the part where it's less than I over 2. Same trick that happened in the first line. In fact, you might actually be able to just say, skip this line and just say this integral is equal to this. It might be obvious to that point, but whoever's looking at this, if they're a stickler for details, then you may as well write it down. It's true regardless. Okay, so what do we do now? Well, we notice that this integral here is the same as the integral over the set f less than or equal to I over 2 f. Man, this is really annoying. I don't know why it's so annoying. It's equal to this guy, but this guy is less than or equal to I over 2. How do I know that? Well, I can replace f in here. You know, I'm just finding an upper bound. So what I can do is I can replace this f with I over 2 to get integral of I over 2 dm. But the I over 2 pops out over here, and then I just get the measure of the unit interval, which is 1. So I over 2 times 1 gives me I over 2. So I have that crude upper bound there. And then basically everything's done. Because then if you so then you have I equal integral 0 to 1 f dm is equal to integral f bigger than I over 2 f dm. Well, if I'm going to get an upper bound, I need to replace it with this. Bigger than or equal to, and then I have I over 2 here. But then I can just subtract this over to the other side. So I have I over 2 is less than or equal to the integral of f dm, f bigger than I over 2. And then what happens? I know that this function has to be less than or equal to, or this integral rather, has to be less than or equal to the measure of f bigger than I over 2. Period. Pretty straightforward problem. I probably could have even done it in fewer steps, but oh well. No one's going to complain if I include too many details. All right, the next problem, we want to find all such p positive such that the following series converges. So this was a qualifier problem from May 2022. This one was, so a while back I made an episode of these real analysis problems, and I showed you one that involved showing that the integral of a function cubed is bigger than or equal to 14. And I said that function, or excuse me, that question was the easiest, but there may have been one other that was easier, and this is the other one. So that qualifier in particular was kind of simple. Kind of wish I had taken that one, but I wouldn't have been ready. All right, so this sum we can write it. And the way we want to write it is we want to group some things together. So the first fraction is going to be 1, 2 to the p plus 1. I already screwed up. Minus 1 over 3 to the p minus 1 plus, and then we'll do another term here just to illustrate my point. We have 4 to the p plus 1 minus 1 over 5 to the p minus 1 plus so on and so forth. And then we have 1 over, at some stage we're going to have n, right? So we have n to the p plus 1. And then we'll have minus n to the n plus 1p, subtract 1, so on and so forth. And we're interested in seeing what happens to this term when n gets really stupidly big. So if we rewrite this term over here, so I'll write 1 n to the p plus 1, subtract 1, n plus 1 p minus 1. I didn't really need to write that, did I? Whatever. So we have n plus 1 p minus 1, subtract n to the p minus 2. By minus 2, I mean minus 1. I skipped a step in my head. So I have that, and then on the bottom, we'll have n to the p plus 1 times n plus 1 to the p minus 1. So all I did was establish like denominators and added them together. Okay, what happens when n gets large? So when n is large, it basically behaves like n plus 1. When n large, n is comparable to n plus 1. I don't know if that's the right notation for that. What I'm saying is there's not much difference between a billion and a billion plus 1. So they kind of behave the same asymptotically. And so when we rewrite this, we'll end up getting this n plus 1 behaves like n, so it cancels with that guy. So we end up with this approximation, so I'll do approximately. We get, what do we get? We get a negative 2 on the top, and then on the bottom, we end up with n to the p, because that behaves like n now. So I have np times np, so I get n to the 2p when I multiply them together. And then I get 1 minus 1, so I get a minus 1 here. But that minus 1 doesn't really make a difference when n is super big, right? Again, we're answering a question about asymptotics. So we have negative 2 on top, and we have n to the 2p on the bottom. And so we compare this to the harmonic series, right? So by the comparison test, or whatever it's called, by comparison test, this guy, which I'll call A just for notation. So A, actually, you know what? Let me spell it out. So let me get rid of this A. I don't need it. So we end up with n equal 2 to infinity of negative 2 over n to the 2p converges when 2p, well, we'll write it this way, converges when 2p is less than 1, which means that p has to be less than a half. Something like that. So yeah, we just take a term, see how it asymptotically behaves when n is huge, and ask ourselves, okay, when does that series converge? And that part's not too hard to come up with. Pretty nice problem. Okay, and now we have one more problem. We have f is integrable over the interval 0 to 1. We want to find the following limit. So we want to take the limit of the integral 0 to 1, k times log of 1 plus absolute value f squared over k squared dx. So this is probably the hardest one of the three, but it's still not that bad. It's as long as you identify the trick that's involved and notice some things, then it's fairly straightforward. So what do we know? What do we know? I gotta quit saying things are straightforward and just do it. So we analyze this integrand a little bit. So what do we say? We say that 1 over k times the logarithm of 1 plus absolute value fx. I didn't write it here, but it's fx squared over k squared raised to the k squared power is less than or equal to 1 over k logarithm. And notice that this, how do I say it? This inner term here, raised to the k squared, that looks like the definition for e to the x, right? But it's e to this thing. So we have e raised to the absolute value fx squared. Because here you can think of this is that term squared, and then you have that exponent up here. So by a change of variables, you can get it to look like e to the fx power. But then again, it's squared. And then that reduces, right? Because if you take the logarithm of e, that will disappear, and then the fx squared comes down in front. So this guy reduces to 1 over k times the absolute value fx squared. Okay, so that's very nice because fx is L1 integrable. And now we make the following remark. So note that the logarithm of 1 plus t is less than or equal to 2 times the square root of t. And that's true for any t positive or non-negative. So why am I doing this here? I'm doing this because I need to find an integrable majorant for this guy, I believe. Yeah, we need to find an integrable majorant because that's going to allow us to pass the limit inside by applying the dominated convergence theorem. So the trick to this problem is using dominated convergence theorem. Okay. Then k times the logarithm of 1 plus absolute value fx squared over k squared. That is going to be less than or equal to 2 times k absolute value fx over k. Because remember, this guy was bounded above by this guy. And this guy... Hold on, now I'm confused. I've confused myself. Oh, because we take the square root, right? Because that gives me this guy. So we're using this fact here and this fact up here to make this claim. All right. And then the k's cancel, and we end up with 2 times the absolute value. Oh my God. Fine. I'm getting agitated. I've had a rough day. 2 times absolute value fx. And that's integrable. So because it's integrable, we can apply dominated convergence theorem. Which means that the limit integral 0 to 1 k log 1 plus absolute value f squared k squared dx k is equal to, and then put the limit inside, dx k. But that limit just tends to 0. So the limit has to be 0 itself. So let's take a second to check our work. That makes sense. That makes sense. That comes down in front. We know that log of 1 plus t is less than or equal to 2 times square root t. So this is like our 1 plus t. So that's going to be less than or equal to the square root of the inside. The square root of inside the logarithm. Or no, excuse me, the t part, which is this part here. So when you take the square root, you get absolute value fx over k. And then this k comes from here, and that 2 comes from up there, and then the 2's cancel. So we end up getting 2 times absolute value fx. Fx we assumed was in this set, so everything's integrable. So allow us to apply dominated convergence theorem. So that looks good, pass the limit inside, and then this becomes e to the f squared. That comes down in front. And then as k... Hold on a second, now I've talked myself out of it. What's tending towards 0? Oh, I'm a stupid. There's this 1 over k here. That k is tending toward infinity. So there you go. So yeah, everything goes to 0. All right, had to pause for thought there. I like this problem. I found it on the internet somewhere, and there have been qualifier-like problems that resemble this, but I haven't seen a problem quite like this on, not exactly like this on a qualifying exam, but I've seen stuff in the neighborhood of this problem, and I think if I was writing a qual, this one would be an optimal problem to choose. It's not super trivial. There is some kind of thought because you need to make this observation here. You need to observe that dominated convergence is involved, and it's also not too long to do. So I like this problem, and I thought I would show it to you. Anyway, thanks again, and I'll see you in a new video.